Hello friends, welcome to Learner's Planet. Friends, this is our fifth session for real numbers. In the previous session, we discussed good number of sums based on HCF LCM. We discussed prime factorization as well as divisor method to find out HCF of two numbers. Then we discussed the formula that HCF into LCM is equal to product of numbers, right? So in this session, we'll be taking more conceptual problems. So let's begin the session. Now friends, let's take up this problem. Show that n square minus 1 is divisible by 8 if n is an odd positive integer, right? Now, see, we have to prove this using Euclid's lemma, right? Now, according to Euclid's lemma, we just know this formula that any dividend is equal to divisor into quotient plus remainder, right? And we know that if I just write this in the context of 4, what I can write that every odd positive integer, I just write over here, every odd positive integer is of the form 4q plus 1 or 4q plus 3, where q is any integer, right? I mean any positive integer, right? Okay. So for any odd integer, we have two methods. Either we write them as 4q plus 1 format or 4q plus 3 format, right? So let's take up the cases individually. First case is when the odd integer is in 4q plus 1 format, right? Now what happens? I just take this integer as any number that is n, right? So this is an odd number that can be written as 4q plus 1 format, right? Now, first of all, let's calculate n square. So n square will be what? 4q plus 1 whole square. So that's 16q square plus 8q plus 1, right? Now, if I deduct 1 from both the sides, because I have to get n square minus 1, so n square minus 1 is 16q square plus 8q, right? Now what? N square minus 1 is equal to, I can take 8 as common, 8q, so it will be 2q plus 1. That means this expression will also be an integer, and this integer is multiple of 8. That means n square minus 1 is always multiple of 8, right? So what was n? N was an odd positive integer, right? As we have discussed over here, right? So we proved that n square minus 1 is divisible by 8, right? This is what the case 1. Now let's take up the next case when the number is of the form 4q plus 3, right? So let's see what happens then. Second case, when the number is of the form 4q plus 3. Again calculate n square. So that's 4q plus 3 whole square. So that's 16q square plus 4 3s are 12, 2s are 24q plus 9, right? Now we have to calculate n square minus 1. So I deduct 1 from both the sides. So n square minus 1 is 16q square plus 24q plus 8, right? 9 minus 1. Now that's, I can take 8 as common. So it's 2q square plus 3q plus 1. Now this will also be an integer, obviously, because q is an integer. So this integer is multiplied by 8. That means n square minus 1 is multiple of 8, or we can say n square minus 1 is divisible by 8, right? So we had proved it for both the cases, right? When n is of the form 4q plus 3, or when n is of the form 4q plus 1, right? So I hope it's clear to you. It's really going to be important, so just learn it or write it for 2-3 times, right? Now friends, let's do this question further. This is an important question. Use Euclid's division lemma to show that the cube of any positive integer is either of the form 9m, 9m plus 1, or 8 for some integer m, right? Now we assume that maybe x is a positive integer. Let x is a positive integer, right? Now we know that any number, that is any integer, is either in the form of 3q, 3q plus 1, or 3q plus 2, right? That means any integer is either multiple of 3, or it leaves remainder as 1 if we divide by 3, or it leaves remainder as 2 if we divide by 3, right? So every positive integer is either 3q, 3q plus 1, or 3q plus 2 format, right? Now we take up the cases one by one. Let's take the first case. Maybe the integer is in the form of 3q. Okay, so x is equal to 3q. That means x cube will be 27q cube, right? That means it is 9 into 3q, right? That means it is 9, or we can say m, right? So it's 9m format, right? Where m is an integer and that m is actually 3q cube, right? So for the first case, it's proof that the cube of any positive integer is of the form 9m, right? Now let's take the next case when x is equal to 3q plus 1 format, right? Now what will happen? X cube will be 27q cube plus 27q square plus 9q plus 1, right? So if we take x cube is equal to 9q is common, so here we'll be getting it's 3q square plus 3q plus 1 plus 1. Now this is suppose an integer m, so this is what 9m plus 1 format. This complete is an integer, right? This is from this, right? So this is 9m plus 1 format, right? So the next, from the next case, that is 3q plus 1 format, if the integer is 3q plus 1 form, then its cube will be of 9m plus 1 format, right? Similarly, let's take up the third case when x is equal to 3q plus 2. So the third case is x is equal to 3q plus 2, right? So x cube will be 3q plus 2 whole cube, that is 27q cube plus 54q square plus 36q plus 8, right? So it's, I take 9q as common, then this 3q square plus 9 6 are, so it's 6q, and then plus 4 plus 8, right? Now this is further an integer, so I just write that as m, so it's 9m plus 8, right? That means cube is either 9m plus 8 format, 9m plus 1 format, this is 9m plus 1 format, or it's 9m format, right? So we have proved that. Okay, I hope you are clear. This is going to be really important, so just revise it 2 or 3 times, so you'll be more comfortable. Okay, now let's see this question. Prove that the product of two consecutive integers is divisible by 2. Now we know that the two consecutive integer, if we take the first integer as x, the other will be x plus 1, right? Or we can say every positive integer is either of the form 2q or 2q plus 1, right? Now 2q and 2q plus 1, both of them are also consecutive integers as x and x plus 1, right? Because if we are add 1 to the 2q, then we get 2q plus 1. That means the difference between these two is 1. That means these two are consecutive integers, right? Now let's assume their product is p. So p is equal to 2q into 2q plus 1, right? So it's 2q into 2q plus 2q. So it's 4q square. It's plus over here, plus 2q. Or further we take 2 as common, then we get 2q square plus q. That's 2m, right? Where m is this quantity. That means this product, that means the product of two consecutive integers is always divisible by 2, right? We got it over here. I hope you are clear. Now friends, let's see next pattern of question. Here, suppose we have to find out HCF of maybe 65 and 117, and we have to express that in the form of 65m plus 117n, right? Now see, how do we find out the HCF of two datas? We just use the division method over here. In the division method, obviously the bigger number should be dividend and the smaller number will be divisor, right? So let's proceed. So it's 117 and it is 65. So 65. So it's 52. That means the remainder is not 0, right? That means 65 is not the HCF of 65 and 117. So how could we write this 117? According to Euclid's lemma, 117 is equal to 65, that is divisor into quotient plus remainder, right? Now we just use this divisor as dividend over here. This way, we have already discussed this. Still the remainder is not 0, right? So how could we write 65 now? From this step, this is divisor into quotient plus remainder. So it's 52 into 1 plus 13, right? Similarly, now we get the remainder as 0. That means 13 is HCF of 65 and 117, right? So that means we can write it 52 is equal to 13 into 4 plus 0. So we got these three relations, right? Now from this equation, 65 is equal to 52 into 1 plus 13, right? So from here I just get the value of 13. So what that will be? Just see it over here. 13 is equal to 65 minus 52 into 1, right? Now I just put the value of this 52 from the other equation or other relation. So from equation 1 we can say 52 is equal to what? 117 minus 65 into 1. So I put the value of 52 from this relation, right? So it's 13 is equal to 65 minus, instead of 52 I just write 117 minus 65 into 1, right? So it's 13 is equal to 65 minus 117 minus 65 into 1. So that's plus 65, right? Now it is 65 plus 65, so it is 2 into 65 plus minus 1 into 117, right? Now we have to present this expression in this form, that is 65m plus 117n, right? So 65m and 117n, that means m is equal to 2 and n is equal to minus 1. I just compare over here. It is 65m plus 117n. So if I make the comparison between these two, m will be equal to 2 and n will be equal to minus 1, right? So this is just an other way of presenting, right? That is, I just express HCF of these two datas in this form, that is of HCF of 65 and 117, right? I hope you are clear. Now suppose let's take the next question. Maybe HCF of 210 and 55 is expressed in the form 210 into 5 plus 55y, right? So we have to find out the value of y, right? Now first of all, let's calculate the HCF of 210 and 55. So how do we do that? We apply division method. So 210 divided by 55. So 55 into 3, that's 165. So we get 45. So remainder is not 0. That means 55 is not the HCF. So we can write 210, that is dividend is equal to quotient into divisor plus remainder. So it's 3 into 55 plus 45, right? Next step, this way, 45 1 45, still the remainder is not 0, that means even 45 is not the HCF. So we write 55 as 45 into 1 plus 10, right? Third step, so 10 4s are 40, we get 5. So still the remainder is not 0. So now we write 45 as 4 into 10 plus 5, right? Now let's proceed further ones. It's 10, so it's 2, 10, that is 0. That means 10 can be written as 2 into 5 plus 0, right? That means in this step we are getting the remainder as 0. That means 5 is HCF, right? Now 5 is HCF and HCF of 210 and 55 is expressed in this format. That means this is nothing but HCF of these two, and the HCF of these two is 5. That means this is nothing but 5. So I just equate it to 5. So it's 210 into 5 plus 55y is equal to 5. Now we just have to solve this equation, right? So it's 55y is equal to 5 minus 210 into 5. So it's 4 into 210, that's 2 negative. So y is equal to minus 4 into 210 by 55, right? Sorry, it is 210 into minus 5 plus 5, right? So y is equal to, if we take 5 as common from these two, so I'll be getting 209 into 5 by 55, and that too is negative, right? So it's 11 and it's 11 1 and 9, so it's minus 19, right? So the value of y is minus 19. Okay, and I hope you are clear. Similarly, we take one more question of this type. HCF of 408 and 1032 is expressed in the form of 1032m minus 408 into 5, right? And we have to calculate the value of m. Okay, now the procedure will remain same. First of all, we have to find out the HCF of these two data, and we have to put the value of this expression as that HCF, right? So let's calculate the HCF. So it's 408 1032. It's 2 times, it's 816. So it's 216. So the remainder is not 0. That means 408 is not HCF. Now for the next step, I just write 408 over here. So it will just go once, deduct 216. So we get 192. Still the remainder is not 0. That means even 216 is not the HCF. Now next step. Now we get 24 as the remainder. Still we are getting remainder as non-zero. That means even 192 is not HCF. Now the next step. Now 24 8s are 192. Now we are getting the remainder as 0. That means 24 is HCF. Right? Now we got the HCF is in this form, right? That's means this and 24, both of them are same quantities, right? So I just equate this data to 24. Just write it over here. 1032m minus 408 into 5 is equal to 24. So let's calculate the value of m. M will be equal to 24 into 408, plus 408 into 5 divided by 1032, right? So it's 2064 by 1032, so it's 2, right? So we got the value of m as 2. I hope you are clear now with this pattern of question also. Now friends, the next pattern of question is, without actual performing the long division, state whether the following rational numbers will have terminating decimal expansion or a non-terminating decimal expansion. So friends, we have already discussed if there is if we do the prime factorization of denominator and if we get the factors as 2 and 5 only, I just write it over here. Prime factorization of denominator, right? If the factors are only 2 and 5, then it will be terminating decimal expansion. That means after decimal 2, 2, 3, 4 maybe, but it will terminate, right? And if the factors are any other number except 2 and 5 or along with 2 and 5, if the factors are other than 2 and 5, then it will be non-terminating. Right? That means in the denominator, what is the first step? We have to go for the prime factorization of the denominators. If they contain only 2 and 5, or only 2 is there, or only 5 is there, or any combination of 2 and 5 is there, then it will be a terminating decimal. And if they are having any other factors, maybe 2 and 5 is also there, but apart from 2 and 5, if they have any other prime factors, then that will be non-terminating, right? I just take this given examples to elaborate this. Wait a moment. Now let's take up this first example, 23 by 8. Here, if we factorize the denominator 8, the prime factorization of this is 2 cube. That means only 2 is there as a prime factor of 8, right? So it will be a term, it will have a terminating decimal, right? Now this is what? 441. 441, it's not multiple of 2 and 5. So it will be having other prime factors from 2 and 5 as well, right? 2 and 5 will not be there definitely. So if we go for the prime factorization of 441, we will be getting numbers other than 2 or 5, right? So it's non-terminating decimal expansion. Here 50, the prime factors contain only 2 and 5, so definitely it will be a terminating decimal. Here, apart from 2 and 5, the factors are 3 and 7 as well. So it will be a non-terminating expansion, right? Over here, apart from 2 and 5, we have 7 also. So again, it's a non-terminating decimal. Okay, I hope you are clear. It's very simple funda. If you have prime factors as 2 or 5 or 2 and 5 in the denominator, then it will be a terminating, and if you have any number other than that, then it will be non-terminating, right? Friends, will be taking more problems, we'll be taking MCQs also and the word problems based on HCF in our next session. So do revise this session before coming to the next session. Bye bye.